welcome to Learning Machines seminars at RISE. Welcome especially Maria Priisalu, who's a PhD student at Lund University. Maria's research is focusing on deep reinforcement learning based approaches, and she's focusing on visually reasoning pedestrian models. She's had an internship at CERN, fellowship at Caltech. She's been an exchange student at Georgia Tech and Zhejiang University. And now she's here to talk about her research. And please, Maria, the floor is yours.
Great. So the talk I'm giving today is called Semantically Reasoning Pedestrian Models in Generative Autonomous Vehicle Testing. So we have quite a lot of grounds to cover. And if you feel like asking a question, please do, because it might be hard to come back to. I will begin by giving an overview of pedestrian forecasting methods. Then we will move on to the ACCV paper that we had in our group on semantically reasoning pedestrian models. Next, I will talk about autonomous vehicle testing, in particular scenario generation for autonomous vehicle testing. And I will give a short introduction to this. Then I will give an overview of the CoRL paper that we just had on generating scenarios with diverse pedestrian behaviors. And in the end, I will give a very brief overview of other scenario generation methods for autonomous vehicle testing. And there's some additional time possibly for questions at the end. So pedestrian trajectory for forecasting, what do we in general mean by that? So assuming that we know the past end locations of a pedestrian in a scene, so X and Y coordinates, we would like to predict the pedestrian's next position or certain number of time steps into the future. We would like to predict the pedestrian's positions. And there are multiple variations to this. So this is the base problem. So the first very common variation is that assuming that we know the past and trajectory steps of a number of pedestrians in the scene, so all of the pedestrians in the scene, we would like to predict the next future positions of the pedestrian. And this means that we're trying to learn how pedestrians interact with each other. And then we might assume also that we're perhaps given the top view of the scene, so trying to model the interactions of a pedestrian with its scene. So this requires some sort of semantic reasoning. We might also consider the case when we're given the pedestrian's goal location. So we might have a two-step model where we first try to predict where is the pedestrian heading, and then conditioned on the heading location, we then try to understand what are the next positions of the pedestrian. We might also consider things like the pedestrian's head location or other visual cues, such as the pedestrian's pose or age or height and so on, to determine the pedestrian's particular dynamics, this individual dynamics, or to understand more precisely what the pedestrian is doing in the current moment. So why is pedestrian forecasting difficult? So this is a bit of a hard to read slide, but bear with me. So to begin with, pedestrians are very stochastic, especially when compared to cars. So here to the right, you can see a sample of a data set with pedestrian trajectories. And even though we see general trends of how the pedestrians are moving, as you can see here, we can see that each individual pedestrian has chosen to do some particular variation of the general path. And because we don't know what is going on in the pedestrian's head, it's hard to predict exactly how the pedestrian will behave and where exactly will the pedestrian end up. Secondly, pedestrians have a certain set of dynamics. So human motion in general has dynamic constraints. So depending on your current pose there, you might be able to achieve a certain velocity faster or slower. So from standing, it might take longer to come to running than from walking, for example. And also each individual has different dynamics and different desired standard velocities. So for example, an elderly person might walk at a slower pace than, let's say, a middle-aged person, or a kid might walk or run and switch between walking and running and still perhaps have an average speed that is lower than a grown-up. Then we have also interactions between the pedestrians, but also interactions with the scene semantics. So pedestrians in general in traffic scenarios tend to be on pavements, for example, but there might be other situations such as pedestrians trying to avoid a certain spot or tending to walk near a certain spot and so on, and this might be scene specific. And the interactions between pedestrians can be either that the pedestrians are trying to avoid collisions, or that the pedestrians are perhaps walking in social groups, so a group of friends. And finally, data gathering can be complicated. So in the perfect world, we would like to know what are the poses of each pedestrian in a complicated traffic scenario. So with cars and with the scene semantics and everything that we have in real life. But this is in general relatively hard to capture, and I'm not aware of any data set that actually has this. So we will begin with some very basic models that have changed the forecasting model world, basically. And the very first model that is still used in modern methods is the social force model. And this assumes that each pedestrian has a desired velocity, so some standard velocity that they always go to. And in addition to this, each pedestrian has a repulsive force on other pedestrians. And in particular, if they don't know each other, but also pedestrians can have attractive forces. So if they're friends or if they for some reason walk close to each other. So this repulsive force is modeled by potential that is ellipsoidal in the movement direction of the pedestrian, and it's decreasing with distance. So the further away two pedestrians are, the less repulsive force there is between them. And there's also this individual stochastic term, the very third point. Oh, sorry. That tells us how a specific individual is acting. As we saw, each individual tended to take some different behavior from the previous trajectories taken by others. And to model this, a simple stochastic term is added. So this model is simply adding up all the forces and then calculating the effect of these forces on the desired velocity. And the final velocity is actually thresholded so that it doesn't exceed the maximum pedestrian velocity to at least somewhat assume true pedestrian dynamics. So this has been a paper from '95, and following this, actually, there's quite a lot of time in between. But in 2016, social LSTM came out, and this paper has affected a large number of papers in the field. So the social LSTM actually builds on top of the social forces idea that we should concentrate on modeling the interactions between pedestrians. And it assumes that only pedestrians that are nearby to a specific pedestrian affect that pedestrian's behavior. So if we look in the image here, every single pedestrian has an LSTM modeling its behavior. And if we in particular look at the pedestrian with the black dot, we can see that its neighbors are some red pedestrian, blue pedestrian, and orange pedestrian, but because the red pedestrian is far away, it is excluded from the calculations. So the hidden states of the LSTMs of the blue and the orange pedestrian are now given to the black pedestrian's LSTM. And these are actually just inputted into the LSTM from the social pooling module. And from this LSTM, we get some sort of a prediction of how is the pedestrian going to behave in the next time step. So there's a lot of work that's been inspired by this, among others, a list here. But we can, in more general terms, see an evolution of the forecasting models. So starting from the social forces model that modeled pedestrians kind of as kinematic systems. Then moving on to recurrent neural networks in 2016, and actually even before this. And then came the boom in generative adversarial networks in 2018. And the reason why these generative adversarial networks were used also in pedestrian forecasting is that we know that pedestrians can behave stochastically. So we would like to predict a number of futures in hope that at least one of them will be true to the ground truth future. There's also coarse-to-fine networks that allow for longer term future prediction. And then also came graph neural networks that we in particular use to model the interactions between pedestrians. So assuming that each pedestrian is a node in a graph. And finally, there's also been some transformer models. I've only mentioned one here, but I'm sure there's plenty more. And this STAR model actually uses both transformers and graph neural networks. And this use of transformers is mostly to attend to which time point and which pedestrian should each pedestrian forecast listen to. But in the light of all of this exciting model architecture, they came out a paper showing that actually a constant velocity estimate can outperform a large number of the state-of-the-arts. And they showed that often actually pedestrian data sets are biased because pedestrians tend to walk in straight lines. So basically all of these state-of-the-art models are simply learning the bias in the data set. And they also showed that using a longer pedestrian trajectory history doesn't necessarily lead to lower forecasting errors because a lot of the data is correlated. And even more recent paper showed that in fact, these social pooling mechanisms and all of these social mechanisms that had been developed, in fact, don't seem to understand what a collision is. And to show this, the authors made adversarial attacks on previous data. So if you look really, really closely, you can see that there's a green line that is the ground truth data, a connected line underneath the red one. And the red is the perturbated data. And we can see the social LSTM's prediction for the red line crossing over with its forecast for this pedestrian in gray. And the ground truth data resulted in a pedestrian prediction that just went straight and the pedestrians didn't collide. And similar behaviors can be seen for also other state-of-the-art models. So social LSTM is no longer state-of-the-art, but it's still such a base model used by everyone. So it's something that everyone understands. Great. So just to mention, there's plenty of other approaches. So in this evolution of forecasting models, most of the models maybe you noticed had this word social in front of them. So that means kind of that they're from the same family of models that use this social pooling idea. But there's also reinforcement learning based approaches. There's multimodal predictions, so trying to predict the different possible futures of a single pedestrian. There's methods that do simultaneous detection and forecasting, in particular targeted for autonomous vehicles, because doing detection and forecasting in the same model results basically in faster computation and faster decisions. So you can see an example of that here. There's also models that use data augmentation to improve predictions. So augmentations of the viewpoint, for example, this SimAug. And there's goal-based prediction methods. So conditioning the pedestrian's future on a certain goal. We don't know where the pedestrian's heading, but we still want to generate a number of realistic pedestrian motions or forecast pedestrian motions to those goal states. And this allows, again, for a longer term future prediction. There's plenty of related work. I had to be very brief here, unfortunately. Let's move on to the ACCV paper. So in this ACCV paper, it's work done by me, Ciprian Paturaro, Alexis Pirinen, who at the time was at Lund University and now is at Rice, and Cristian Smincescu. And here you can see a sample trajectory that we generated. So the paper is called Semantic Synthesis of Pedestrian Locomotion. So the problem that we're trying to solve is that we're trying to generate 3D articulated pedestrian motion in complex traffic scenes in a way that is semantically plausible. So you can see here the scene semantics. So the pedestrian should at least assumably tend to stay on pavement. The pedestrian should also avoid collisions with people and cars and other objects, and it should have plausible dynamic varying human locomotion. To do so, we present a hierarchical model that consists of a higher level trajectory planning model, this semantic trajectory policy network. that conditions its next step on the scene semantics and the goal. So it decides in which direction should the pedestrian move. And a lower level 3D human locomotion model, this human locomotion network here, that executes the motions that were proposed by the semantic trajectory policy. And the models are trained using a mix of supervised and reinforcement learning. So to begin with, let's take a look at the environment representation. We reconstruct the scene in 3D and add semantic and RGB labels to it. So semantic segmentation and RGB labels from images. And we also construct a dynamic 3D occupancy map which contains the external cars and pedestrians in the scene and their past motion up to this point. And our pedestrian has a position X. And around this position X, which is marked by this light blue cross here, it observes a local neighborhood marked by the yellow box, bounding box. And for each position that the pedestrian has, it receives a reward. But also this state is given to the semantic trajectory policy, which then uses this state to decide what direction to move in next, or how big should the step in the next time step be. So VT is a velocity. And the human locomotion network then executes this velocity step by giving out a sequence of skeleton poses. And the skeleton poses then give rise to a new updated position of X. So one single VT can equates to actually multiple poses. And why is this an interesting problem? So a lot of the traffic data sets that exist actually model pedestrians as bounding boxes. But the human pose has a lot of motion cues that are not present in bounding boxes. So just by looking at a human skeleton, we can tell if a human is running or walking. And this information is lost when we're simply looking at bounding boxes. So you can see here, it's harder to predict the motion of the bounding boxes rather than the motion of the skeletons. So one way of achieving this is to augment existing traffic data with skeleton poses and training autonomous vehicles to actually use also skeletons or human poses instead of the current bounding boxes to improve their trajectory forecasts of pedestrian motion. And how could this be done? So given a scene, our model can be applied in the scene and we get out a sequence of poses over time. And to each pose, we can apply a dense mesh that is conditioned on the pose. And there exist models for this, like simple. And then we can project that dense mesh onto the image plane to get a semantic segmentation map. If we then want to create RGB images, we can also apply some style transfer. This is obviously a harder problem. And to produce LiDAR data, so if we have a LiDAR traffic data set and we would like to augment it with these pedestrians, we can sample from this dense mesh. So returning back to our original problem definition, we had multiple different objectives. And let's take a look at how we achieve them. So to begin with, we wanted to forecast the pedestrian's next location given its past trajectory and current state. And this is achieved by using supervised learning. We also wanted to learn semantic sensitive behaviors, but ones that are actually not present in the data set, such as collision avoidance, because we basically never see any collisions in traffic data sets, in particular with pedestrians. And this is achieved through reinforcement learning. And finally, we wanted also our model to have realistic human motion. And this is achieved with the human locomotion model that is trained on data gathered in the lab and then deployed outdoors. So let's take a look at the model components. We had the higher level planner, the semantic trajectory policy network, that is both trained to minimize the prediction error of the forecasting task, so the trajectory forecasting task, and to avoid collisions in near collision states. And this is done with reinforcement learning. And the two objectives are unified as one reinforcement learning objective. Then we have the human dynamics model, the human locomotion network, that takes a step to the next trajectory location with realistic human dynamics, but also provides the poses for that step. And finally, we have a reward function that allows us to learn in states outside of the training data set, so outside of the trajectories that are in our training data set for the pedestrian. So let's take a look at the reward function. So we construct our reward such that it obtains its maximum on the ground truth trajectories. And this is one of the requirements for us to be able to combine the policy gradient and the maximum likelihood objectives. So more specifically, what are the reward components? We give a positive reward for visiting pedestrian trajectories. We give also a positive reward for pedestrians visiting locations that often tend to be visited by pedestrians. And to measure this, we approximate the pedestrian distribution with a kernel density map that is based on the ground truth data, D. And we also penalize collisions. And in fine tuning, we also penalize large, very large motions that cause extreme changes in pose. Now, to train our pedestrian trajectory forecasting model, both on supervised data, or in a supervised fashion on the ground truth data, but also on states outside of the training data, we suggest a general framework. And in this general framework, any maximum likelihood trajectory forecasting model can be used. And we do this by reformulating the maximum likelihood objective, which you can see here, as a policy gradient Monte Carlo estimation, which you actually also can see in the same equation. And so writing these two in a single equation, and this is assuming that the reward function obtains its maximum at the ground truth trajectories, we can now jointly maximize the likelihood of the data, but also the expected cumulative reward. So we can train both on the data, but also on states outside of the ground truth data. And in this general framework, our semantic trajectory policy network can be replaced with any trajectory forecasting model. And we can still keep the human locomotion network, as this ensures that the steps suggested by the trajectory forecasting model are plausible according to the human dynamics. And using the reward function, we can then train this trajectory forecasting model both on ground truth data, but also in states outside of the ground truth data. And if we quickly compare this to some inverse reinforcement learning methods, behavior cloning, or actually just supervised learning, means that we're simply sampling on the ground truth data. And this would result in no collision avoidance behavior because we never see any collisions in the data sets used, for example, here. Also, if we would use a method such as Gale, even though we don't sample from only ground truth data, we sample close to it, we would not be able to train in situations that are close to a collision because these are very far away from the ground truth data, and it would be trivial for the discriminator to distinguish this generated data from ground truth data. And now quickly about the human locomotion network. So this is a phase function neural network producing the 3D human body joints to execute a step. And it's conditioned on the past poses of the pedestrian and past motions of the pedestrian, but also on the future or next time step motion of the pedestrian. And this is trained on motion capture data gathered in the lab because it's hard to gather motion capture data outdoors. Okay, and if we look quickly at some results, we can see that our model outperforms at the time state-of-the-art models in collision avoidance. And it even outperforms ground truth data in collision avoidance because of this reinforcement learning that we're doing in near collision scenarios. And if we look at forecasting error, it's the second best on both of the data sets, but the models that perform the best So on the Waymo dataset, it's the behavior cloning. It actually performs the worst on the CoRL dataset, and vice versa for this STGAT. And some sample trajectories, you can see the pedestrian starts underneath the orange arrow and crosses the street. And it managed not to get hit by anyone while crossing the street. So this is real data from Waymo that is with the LiDAR, gathered with the LiDAR sensor. Oh, it's the same trajectory, sorry. Yes, so here again, you can see the pedestrian. And now we can see the pedestrian crossing, and it will wait for the red car to pass. And now comes this green car, and as the green car starts driving towards the pedestrian starts running away, showing that we have learned collision avoidance. And finally, a sample trajectory showing that we can cut corners. The pedestrian model can cut corners and avoid collisions with other pedestrians when crossing, for example. Great. We also developed a goal reaching model. So simply conditioning the semantic trajectory policy network with a goal location and rewarding it for reaching goals. And during supervised training, the goal is the end point of the ground truth pedestrian trajectory. And some sample results of this. So the pedestrian is initialized with the yellow bounding box, and it runs towards the white cross, which is its goal. And the idea with this goal reaching behavior is that if we wish to augment existing data sets, then we have more control over the synthesis of the pedestrian motion. So we can generate multiple futures for the same trajectory. Great. So now we get to talk about autonomous vehicle testing. So I'll give a quick introduction to that. I'll just check on time. Perfect. So to begin with, there are multiple autonomous vehicle models. So we have hierarchical models and end-to-end models. So assuming that we have some sort of waypoint, so not looking at a higher level map, we can either have a model that is in charge of perceiving the pedestrians and the cars in the scene and forecasting their motion, and then a motion planning module that, depending on these forecasts, then decides how the autonomous vehicle should behave. And finally, vehicle control that decides what steering to use to follow the reference trajectory. Or we can have end-to-end models that go all the way from RGB to steering. So just quickly, autonomous vehicles have multiple ways of perceiving the world, especially visually. And the most commonly used visual sensors are cameras or LiDAR sensors. So there's multiple data sets using cameras. Here you can see samples from the cityscapes data set, so the semantic segmentation and the 3D reconstruction that is done with the disparity map, which is not so great, as the depth estimates in a disparity map are not so great. Or the LiDAR data as an alternative. And often we actually have both cameras and LiDAR in more and more of the modern data sets. So what are the limitations of using these kinds of general traffic data sets for autonomous vehicle testing? As I said previously, collisions are extremely rare. So it's hard to evaluate how an autonomous vehicle would do in a near collision scenario or if a collision occurs. And here on the bottom, you can see the frames from actually the fatal Uber crash of 2018. And this is probably something that we hadn't seen in some previous data set, and we hope not to see. There's also problems with limited variability. So in the perfect world, we would like to see a large number of different scene scenarios. We would like to see a large variation in the density of pedestrians and cars. We would like to see a large variation in the visual qualities of the data. So data gathered during the day and night. And finally, data gathering is time consuming. So gathering all of these variations is very time consuming. But fortunately, there's a solution. We can just generate traffic scenarios that are in particular hard for the autonomous vehicle. So the general idea is that we would, in some way, like to generate difficult scenarios that test the autonomous vehicle's safety. And we can define this more precisely depending on what kind of safety we're trying to evaluate. And the general idea is that we're maximizing some cost that the autonomous vehicle has by choosing some parameters or the setup of the scenario, or even the motion of the other agents in the scenario. Great. So I will quickly talk about the CoRL paper, and then I'll give an overview of some other scenario generation methods. So this was work done again by me, Alexis Pirin, and Ciprian Baturaro, and Cristian Smikisescu. And this work was presented at CoRL. So to begin with, we would like to generate scenarios for autonomous vehicle testing. And in particular, we would like to generate traffic scenarios that test the autonomous vehicle's ability to avoid collisions with pedestrians in this case. And here, by an autonomous vehicle, we mean the full pipeline of a hierarchical autonomous vehicle model. So all the way from sensor output to steering, or alternatively, the full pipeline of an end-to-end autonomous vehicle model. So prior work in scene generation for autonomous vehicle testing has considered only the absolute worst case scenarios. And they've done this by using heuristic pedestrian models, so constant velocity or adversarial pedestrians. But a constant velocity pedestrian would mean a pedestrian that ignores the autonomous vehicle all the way down to a collision. So even as the car is hitting the pedestrian, they're ignoring the car. The adversarial pedestrian, on the other hand, would be a pedestrian that wants to get hit by the autonomous vehicle at every single time step. It's doing everything it can to be hit by the autonomous vehicle at every single time step. And we're wondering, is this really likely to occur? Most likely we will have some sort of variations. So perhaps we would like to consider which situations are actually likely to occur. And to this end, we suggest that an autonomous vehicle should be tested on a diverse set of pedestrian behaviors. And the reason for this is that autonomous vehicles will encounter various pedestrians in real traffic. They will encounter kids who might run around and be unexpected. It might encounter distracted pedestrians who at times maybe look up and then react to the autonomous vehicle. It might encounter intoxicated pedestrians who might be hard to predict, but it also might encounter law-obedient pedestrians who do everything to avoid collisions. And the autonomous vehicle should be able to avoid collisions with all of the pedestrians. So in testing, we should also test the autonomous vehicle with all of the pedestrian behaviors. And to this end, we propose a framework that allows the autonomous vehicle to be tested with any goal-driven pedestrian behavior model. So to do this, we reformulate the problem. So in general, in previous work, what has been considered is learning what a pedestrian should do to be colliding with an autonomous vehicle. But instead, we learn where to place pedestrians such that the pedestrian and the autonomous vehicle collide. And after this reformulation, we can now use state-of-the-art pedestrian motion models. So just quickly, our adversarial test synthesizer is what we're learning. So this is the module that places out pedestrians in the scene. And it observes the full scene together with the autonomous vehicle and the autonomous vehicle's goal. And depending on this, it chooses a location to place the pedestrian. So we can say that it's, for example, this pedestrian number 2. And this pedestrian is given a goal that is on the opposite side of the autonomous vehicle's trajectory. And then we perform a rollout following the pedestrian behavior model pi and the autonomous vehicle model rho. And if a collision occurs, then the adversarial test synthesizer is rewarded for this. And eventually the adversarial test synthesizer should learn where to place pedestrians such that collisions occur. So going back to this reformulation, just to understand why we can have any pedestrian behavior. So previously what has been considered in particular in the adversarial pedestrian case, is that we have some autonomous vehicle and some pedestrian. And assuming that rho stands for the adversarial vehicle and theta is some parameterization of the pedestrian's trajectory, and assuming that we can then separate the loss of the autonomous vehicle into terms such that one of the terms is the expected number of collisions with the pedestrian and some other loss terms, where I is the indicator function for collisions. And assuming that we can do a similar rewriting for the loss of the pedestrian, we can see that the autonomous vehicle is minimizing the number of collisions, while the pedestrian is maximizing the number of collisions in the suicidal or adversarial case. We can then rewrite this. So instead of using theta to describe the pedestrian's trajectory, we separate the pedestrian's policy, so the action it takes at every single time step, from its initial location distribution. And we get two equations then describing the pedestrian. So we get one describing the pedestrian's initial location. We're again maximizing the number of collisions. And pedestrian behavior is now again chosen such that it maximizes the number of collisions. But because we do get two different equations, we can now interchange the second equation for the pedestrian policy pi for any loss function. So now we can use state-of-the-art pedestrian motion models. And in particular, we can also look at pedestrian motion models that minimize collisions. And we are the first to actually show that this problem with where the pedestrian is minimizing the number of collisions has a non-trivial solution. And I should mention that in the paper, we also include constraints here, because the reason why we can find a non-trivial solution is that there are enough constraints. So in effect, we show that collision avoiding pedestrian models can be used in autonomous vehicle test case generation. So a look at our model, just checking on the time. So our model is conditioned on the scene semantics to ensure semantic plausibility. And this is because pedestrians have certain tendencies to be in certain areas of the scene. And to be able to learn this, we reward the adversarial test synthesizer for time steps that the pedestrian tends in areas that tend to be visited by pedestrians. And secondly, this prior can be multiplied with an occlusion map from the autonomous vehicle's point of view to enforce that pedestrians are only initialized in locations that are occluded from the autonomous vehicle's point of view. And this means that a pedestrian cannot simply appear out of thin air. So taking a look at some of the results, here you can see the top view of the scene. So we have a prior distribution. And this is needed because otherwise, if we start sampling from a uniform distribution, we simply don't observe any collisions. So this is the prior of the pedestrian initial location distribution. And in green, you can see the autonomous vehicle. In blue, you can see the external cars. And in red, you can see some external pedestrians. And what we can see here after learning, our model has learned some specific distribution for where to place pedestrians. And we also have some certain constraints that the prior is 0 within a certain distance of the vehicle, which is actually the braking distance of the vehicle. So we calculate the braking distance depending on the speed of the autonomous vehicle. And now looking at some of the results when we vary the pedestrian model, we can see that using a collision avoiding pedestrian model doesn't actually decrease the number of collisions we can generate when compared to the adversarial pedestrian model. And the reason, because we would expect the adversarial pedestrian model to result in more collisions than the collision avoiding pedestrian model. And the reason why we think that this is the case is because the collision avoiding pedestrian model has a lower entropy because it's been trained on pedestrian priors. So the initializer model has more control over the pedestrian, while the adversarial pedestrian model does things like zigzagging in the middle of the street to get hit by the car. And the constant velocity pedestrian model actually results in the fewest number of collisions. And we think that this is because the constant velocity model is so predictable. So even a very simple autonomous vehicle model can forecast this pedestrian's motion and avoid collision with it. So conclusion is we can use any goal-driven pedestrian model in this framework. So some sample results. So these are samples from the prior, so before training. And remember the pedestrian is initialized here. So the goal is its reflection in the autonomous vehicle's trajectory, so on the other side of the vehicle. And we can see here using a collision avoiding pedestrian. So the pedestrian I presented to you previously, the ACCV work, it chooses to actually just walk towards pavement because it's safer there and ignore its goal. And we see a similar behavior here. The pedestrian is walking straight because there's another car coming here. And another sample showing similar behavior. So again, the pedestrian prefers to be on pavement. And now after some training, our model actually learns to use the blind spots of both the pedestrian model and the autonomous vehicle, resulting in collisions. And because we are learning a distribution, sometimes we sample pedestrian initial locations that are far away from the autonomous vehicle. And in this case, there's nothing that the pedestrian initial location distribution can do to enforce a collision. And even sometimes when the pedestrian is initialized close to the vehicle is so good at avoiding collisions or just speeds away simply. So there's nothing that the adversarial test synthesizer can do to generate the collision. So our code is available on GitHub for both of the projects. And finally, a quick overview of scenario generation methods. Let's see, it's 42. So I will jump actually to simply the overview of methods that have been used. So there exist black box optimization methods for generating autonomous vehicle test cases. And this is because we don't know where the cost function of the autonomous vehicle obtains its maxima. So we simply treat this, we don't actually know anything perhaps about this cost function from the perspective of the scenario parameters. So we treat this as a black box. There's also reinforcement learning methods, and there's two types as far as I've seen. There's probably more methods where reinforcement learning agents design the environment to be challenging for the autonomous vehicle. And this is the case you can see in the top figure here. So the solver would be here, the reinforcement learning agent that chooses some environmental parameters, and then we evaluate in simulator the outcome. And also there are methods that use reinforcement learning agents to model traffic participants. So perhaps modeling the other cars or pedestrians quite often with an adversarial reward. There's also adversarial attack methods. So adversarial attacks to choose an adversarial environment. So choosing things like the weather or in simulation or perhaps even the geometrics of the scene or so on. And there's also methods that look at adversarial changes to data. And the reason why this is something that people look at is that we can then use ground truth data and we don't have this simulation to real gap. So this is an example here. Let's see. The perturbed vehicle is the red one. So we can see, for example, they can generate a collision by moving this red vehicle to a new position. And there are also planning-based methods, so classical methods that simply plan out the future of the autonomous vehicle and use some model to model the pedestrians and other vehicles and find situations where this leads to a collision. There's also dataset extrapolation and interpolation methods. Great, so I think I will stop there. Questions?
Thank you for this talk, Maria. Do we have some questions? Could you imagine using sort of your generated scenarios to train other models?
Yeah, definitely. So I think this is something that is actually being looked at also in robotics. So when you have robotic hands doing certain actions, if they're interacting in particular with humans, what would the human need to do then to affect the robot in a negative way or even hurt the robot in some way? Yeah. So this is something that is definitely usable anywhere, right? So, yeah.
What would some hurdles be for using your techniques for that?
I haven't thought about it, to be honest. I'm thinking.
Yep.
I'm not sure that our reinforcement learning method would be of interest then, because you have a very specific problem probably with very specific outcomes. While the reason why we chose a reinforcement learning method was that, I'll just jump back, we had, the generation was conditioned on the scene. So we allowed the scene to vary. But if you're in some sort of manufacturing setup, maybe you don't have that large of a variation in the setting. So maybe a black box optimization method would be even faster because you can exhaust the search based faster. Yeah, but I'm not sure. Any other questions from someone else?
Yeah, I have one. In the beginning, you showed these models that showed the pedestrian behavior around like an intersection. I think it was a Waymo dataset. And the models you learned there, are they transferable between locations, or is it like one location per data set and you sort of learn it specifically for that location? Or can you just apply it in any intersection or any street?
You can apply it anywhere. Oh, sorry. So I think you meant these ones. Yeah, these are trained with like 100 different scenarios or scenes. Or yeah. So it should be, I mean, assuming that it's quite similar to this current data set, so you should be able to transfer it directly.
Yeah. And are these data sets freely available?
So the Waymo data set is, and also the CoRL data sets are, we are unfortunately not able to release our variations or the modifications we've done to the data set because of the ways the data sets have been released. So we use 3 data sets, CoRL, Cityscapes, and Waymo, but all of the code for reconstructing the data sets is available.
Okay, well, that's cool. Thank you.
Yeah.
I had a question. Hopefully you can hear me.
Yeah.
So with respect to the reward function for the pedestrians in terms of generating, or rather the reward for pedestrian behavior. So was it possible, or would it be possible to kind of have a kind of a regularizing term so you can control how suicidal the agent is?
Oh, you're talking about this adversarial test synthesizer.
Yeah.
So yes, you would be able to add a term like that because we separate this pedestrian behavior model from the initialization. So we actually showed just the extreme cases of a collision avoiding pedestrian and a collision seeking pedestrian, but you can have any variation in between.
Yeah.
Definitely.
Okay.
Yeah.
Okay. I guess that's how you would want to build a synthesizer, I guess, because if you sample too much from the suicidal ones, if you also train the vehicle in the same setting, it will be a very careful vehicle, I guess.
Yeah, I guess so too. So I think in general, you would just need to test it with variety and see what the vehicle does.
Yeah. All right, thank you.
Great. Any other questions?
Well, I could throw in another one. In the end, also in this testing scenario, the adversarial pedestrians, you showed the videos, they only showed one pedestrian at a time. I'm imagining that it could be quite a lot harder to handle lots of pedestrians in the scene for the car, especially, let's say, a group of children, you know, wanting to cross the street and stuff like that. So yeah, I mean, maybe you could take it from here. Just It seems like you've thought about that before.
Yeah, we've thought about it. So it actually becomes an easier problem, because if we look at this case where we had collision avoiding pedestrians, they are trying to minimize the number of collisions. But what the test generator is trying to do, it's trying to maximize the number of collisions. And if we have more pedestrians in the scene, then we have more physical constraints for the autonomous vehicle. So it has fewer options of, running away. It cannot just speed away if it has a cluster of pedestrians, blocking its way. So it actually becomes an easier problem, but perhaps in practice, it might be a harder problem, right? So in theory, it's an easier problem, but in practice, it's probably harder.
Okay, thanks.
Yeah.
I assume the same, at least the reward function could be used for other agents than just pedestrians, I guess.
Yeah, I think it can be transferable because our reward function is quite general. We simply reward collisions and behaviors that are similar to pedestrians, so according to some density map estimate. And you could do that with any kind of motion if you have some model of what you would like to kind of mimic and at the same time reward collisions.
Yeah. Okay, thanks.
Yeah.
Any last question? Otherwise, we'll thank Maria with a virtual hand. Thank you for this talk. Next week, we'll have Ebba Ekblom from RISE talking about federated learning and generative adversarial networks. So see you in 1 week.
Thanks, Sam. Very interesting research, by the way. Thumbs up.